Morning, everyone. Welcome to this week's IQS seminar. We have Dr. Paolo Andrea Erdman today with us. Paolo did his master's and bachelor's in University of Pisa. We did our PhD together at the Scuola Normale Superiore with Fabio Dadde and Rosario Faccia. Now he's a postdoc at Free Universität Berlin with Frank Noe, and he's visiting us this week. So, Paolo, the floor is yours.
Thank you, Vivek. Yeah, hello, everyone. Thank you for being here, and thank you, Vivek and Andrew, for the invitation. It's been a great visit so far, so yeah. Today I was thinking of kind of trying to give an overview of what I've been doing in the last few years since I started my postdoc, which roughly can be summarized as using machine learning methods in the field of quantum thermodynamics. So the work I'll talk about was done also together with people at the University of Geneva, at Collège de France, and Scuola Normale. So yeah, as an outline, first I'll just motivate or explain a little bit what is quantum thermodynamics and why we want to use these methods for it. Then I'll talk mainly about two different approaches. One is the optimal control and the optimal design of quantum devices, and I'll explain better what I mean. And in the optimal control approach, we'll see how we use reinforcement learning to optimally control quantum heat engines and quantum batteries. And in the optimal design case, we'll see how we can design, let's say, an optimal quantum thermometer. And I'll explain all these concepts better, what I mean by them. Okay, so I guess as you all know, machine learning has been really successful in a number of fields. So for example, for image recognition, for natural language processing, for example, ChatGPT or Gemini and all these new approaches. It's also been used a lot in recommendation systems or to play video games and so on. And what about science? So in the last few years, I would say maybe 6-7 years, it's been applied a lot also in science. For example, in this review in 2022, they showed the number of papers that use machine learning in chemistry, physics, and material science. And there's really this kind of sharp increase since maybe 2017, 2018. And specifically in quantum physics, also, there have been many applications. It's been used, for example, for quantum state tomography, so how to reconstruct a quantum state from the measurement outcomes. Been used for quantum state representation, to build very flexible ansatz to represent a wave function classically. Been used to do phase classification, so to distinguish, for example, the phase of matter by just looking at the system. Even to design experiments, so to design, for example, optical setups to implement a given experiment, like I think even to verify the Bell state inequality and so on. It's been used for quantum control, so to steer quantum systems using, in this case, we're also using reinforcement learning to learn the Hamiltonian from observing the dynamics and so on. So there are many approaches. So what I'll focus on is more the use of machine learning and quantum thermodynamics, that it's arguably been less studied also because quantum thermodynamics is probably a smaller field compared to quantum computation, but there's still, I think, quite a few things one can do. So what is quantum thermodynamics? I guess in a nutshell, it can be described as the application of thermodynamics at the nanoscale. So thermodynamics was developed with large system in mind, so with macroscopic objects, gases, and liquids, and so on. And now people are trying to understand how do you apply these concepts to something that is really small, so to this few electrons or few atoms, few ions, or even something as small as a qubit. So from a fundamental point of view, there's a line of research even trying to understand how to state the laws of thermodynamics at the nanoscale when maybe systems are strongly coupled to each other. Or one can study, for example, the dynamics of energy, heat, and charge in nanostructures, so in very small devices. And one interesting consequence of studying thermodynamics at the nanoscale is that you could have large fluctuations in the thermodynamic quantities, which is maybe something less intuitive that doesn't happen in macroscopic systems. And from a slightly more, let's say, applicative point of view, one can also try to understand if we could make devices something like the equivalent of a heat engine, but at the nanoscale, so exploiting potentially quantum effects. Or if we can study quantum systems as batteries, so if we can study the dynamics or the transfer of energy between quantum systems and their storage. And this is mainly what I will be focusing on. Okay, so in general, as I was saying, I consider the optimal control and design of, let's say, these quantum devices. And the optimal control setting, what you have in mind is that there's some open quantum system, open in the sense that it's coupled to some environment. And this environment could represent a hot and a cold thermal reservoir or something else in principle. And importantly, we have a set of time-dependent controls on our system. So if the system here in the center was a qubit, we could maybe tune its level spacing. So we could choose, for example, the gate voltage or some magnetic field or some control that we have over the quantum system. And we assume that the dynamics of the system is assigned. So for example, this is the Limelight equation, which would represent the evolution of the state of the open quantum system in the presence of the environment. And we assume that this is given. And what we want to solve is how to learn these time-dependent controls to achieve a certain goal. So if you imagine, for example, it's like having a car and you want to learn just how to drive the car, and you don't look how the car is made inside, let's say. Instead, in the optimal, let's say, design case, what we have in mind is, again, some open quantum system, but now we assign some structure to it. So we consider, for example, a large class of Hamiltonians. We assume that there could be one-body terms plus two-body interactions, and we keep all these parameters to be general. And then our goal is to kind of determine how to design these connections, so these interaction between the nodes, and how to design these local fields to obtain a certain, again, a certain goal. Okay, so we'll start with the optimal control of quantum heat engines or thermal machines. So what we focus on was driven thermal machines. So from an abstract point of view, even in the classical case, what we have in mind is something, so we have some system, and then we have a hot bath and a cold bath. And in time, we can decide to couple the system to the hot bath and exchange some heat. We can couple it to the cold bath and exchange some heat with the cold bath. And again, what's important is that we have these time-dependent controls. So in this classical case, if this is a piston with some gas inside, our control could be, for example, the position of this piston. And if we act on it, so if we allow it to expand, we can exchange work with it. So this is how we can exchange work in a open, in a driven thermal machine. And we could also influence the state of the system. And then we could study, for example, the heat engine. So this is where we want to extract work from a temperature difference. Or we could study the refrigerator, which is where we want to extract heat from the cold bath by putting work into the system. So what we want to do is kind of study, let's say, the quantum counterpart of this would be to replace this gas with some quantum system. And also the reservoirs would be something miniaturized. And then I'll show some examples of experiments where this idea has been kind of tested. And the main difference, I would say, is the regime in which we're operating. So classically here, you would have something like a macroscopic system with an Avogadro number of particles. So the state of the particles will always be close to equilibrium. You don't have to solve the dynamics of every particle, but you can describe it in terms of like pressure, temperature, volume. And typically, you would have small fluctuations in the quantities. And kind of in the opposite limit, we're dealing with something with just very few degrees of freedom, maybe single ion or few electrons, or even something as small as a qubit, which is just a two-level system. So we have, few degrees of freedom. And because of this, the state of the qubit can be driven, or of the system can be driven far from equilibrium. So we really have to solve the full, let's say, quantum dynamics of the system, and we don't use any effective description in terms of, let's say, volume, temperature, and so on. And we could also have larger fluctuations due to the fact that we have few degrees of freedom. And yes, and let's say solid state platforms where these ideas are being tested are the following. So this is a device that was fabricated in the group of Jukka-Pekkola in Helsinki. And here in the center, this is a transmon qubit. So it's this would be our quantum system or the gas, let's say in the classical case. And here on the side, they have two resistors, and these two resistors have a different temperature, and they're coupled to the qubit. So they can exchange heat in the form of microwave photons. And then they have this additional line here that can allow to control the level splitting of the qubit. So here they have this time-dependent control. Here they have the reservoirs, and they can also measure the heat flowing across the device by reading the temperature drop in the resistors when the heat is flowing. Then another example would be, let's say, thermoelectric devices. This is not a driven case, but still we have here, this green line would be an indium arsenide nanowire. And if you zoom here in the center, this is like 20 nanometers. They embedded these two layers of indium phosphide that behave like as insulators, so they can really confine an electron in this very small region of space. And this is kind of the definition of a quantum dot. So it's a region where you squeeze electrons, and because of the spatial confinement, you have discrete energy levels. And in this device, you could apply temperature difference. And this temperature difference could drive a charge current against a voltage bias. And this is a way of getting work from a temperature difference. This is steady state, but it's still, let's say, using a quantum system at the center. And another experiment is the following, and let's say using trapped ions. So here, yeah, they could trap using laser as a single ion. And by changing in time the confinement of the single ion, you could do the equivalent of like compressing and expanding a gas. And in the same way, you could implement something like an Otto cycle by, let's say, compressing and expanding a single ion that is trapped with these lasers. Okay, mathematically, how do we describe these systems? So we kind of assume that the full system plus the reservoirs obeys unitary dynamics. So we assign a Hamiltonian to the full system, and we have one term that describes our system, for example, the qubit, and this depends explicitly on our controls. And we have one term describing the heat path and one term describing the coupling between the two. And okay, if we make some approximations, for example, we assume that the coupling is weak and that we're in this Markovian regime, one can essentially find this effective description of just the state of the qubit, but in the presence of the heat reservoir. And this would be this Lindblad equation to describe the dynamics of this open quantum system. And okay, so now from a thermodynamic point of view, if we imagine that we change these time-dependent controls in a periodic way, we could implement the equivalent of a thermodynamic cycle. Because, for example, we can, in the ion case, we can compress and expand the particle, or we could change the qubit gap in time. And if we do this in a periodic way, we can implement a thermodynamic cycle. And once we have this, how do we characterize its performance? So we could look at the power, that would be simply the work extracted over one cycle divided by the period, so the duration of the cycle. We could look at the efficiency, which is the extracted work over the input heat. Or equivalently, we could look at the entropy production that we have in a closed cycle. And what is interesting that is in these kind of systems, we could also have fluctuations of the power. So every time you repeat the cycle, since you have such a small system, the power can fluctuate. But I won't talk too much about this in this presentation. And the main question we want to answer is what functions UDT? So which cycles optimize these quantities? So we know that, I guess it's quite intuitive, that there's a trade-off between power and efficiency. So if your car is really powerful, it'll typically be inefficient, and vice versa. So the question is, how do we how do we define even an optimal protocol if there's this trade-off between two objectives, between two quantities? So we use this concept of, let's say, Pareto optimality. So this is, by definition, these are all the cycles where you cannot further improve one quantity without sacrificing the other one. So now we don't look for a single cycle, but for a collection of cycles that are optimal in the sense that there's no other cycle that is better from both points of view. And in practice, to find them, okay, if this Pareto front has certain properties, you could find it simply taking a linear combination of your objectives. Here in our case, it would be to have high power and low entropy production. And then you weigh them with this coefficient A, for example, between 0 and 1. And when A is equal to 1, for example, you're just maximizing the power. When A is equal to 0, you're just minimizing this entropy production. And for intermediate values, you will find these kind of intermediate trade-offs between the two quantities. Okay, so to kind of summarize, with UDT, we describe a cycle. From there, we can compute the state, we can compute its power, average it, and our goal is to find which of these cycles or these protocols maximize the performance of the system. So there have been many approaches in literature. I think I can't review them all, but in general, some papers fix the structure of your cycle. So you fix a given shape of this UDT, which would be the equivalent of choosing, let's say, an Otto or Carnot cycle. People have studied the slow or fast driving regime, so where the driving is fast or slow compared to the time it would take to thermalize the system. There have been approaches where people take cycles that work well in the adiabatic limit and try to study them at finite time using these so-called shortcuts to adiabaticity. Also, variational approach has been proposed, but arguably all of these approaches, except for actually the variational ones, do not guarantee that we will actually find the best cycles, or they're all in some approximation. So what we wanted to do is to have a numerical tool. So it's not analytic, it's just a numerical tool, but that at least allows us to find cycles without making any assumption on what is the shape of this UDT. We don't want to make any assumption on the speed of the driving. In principle, we could even apply this mechanism directly to a system of which we do not know the equation of motion. So we could even have this reinforcement learning interact with an experimental device and kind of learn how to drive it without actually knowing how it really works. In principle, it can also naturally handle noise in the control. So it's a pretty robust way to find, let's say, these optimal cycles. So I'll just say a little bit about what is this, what is reinforcement learning. So this is a collection of algorithms or techniques that allows to solve optimization problems that are formulated in this way. So we have a computer agent that wants to learn how to master some task by interacting with some environment. So we imagine that we discretize time in time steps, and in every time step, the computer agent can choose some action to apply on the environment. And then we receive as feedback what is the state after we apply our action. And we also receive the reward. And the reward is just a number, it's a quantity. And the goal of reinforcement learning is to learn how to choose these actions such that you maximize the sum of the rewards that you will obtain in the future. So if you imagine, I don't know, that this is the chess game, the action would be how you move the chess pieces, the state would be the position of the chessboard, and the reward could be, for example, 0 if you don't win, 1 if you win, or -1 if you lose, or something like that. And typically here one has the sum of the future rewards weighed by this factor gamma to the power I, where gamma is just a number that kind of determines what is the time scale of our optimization. So if gamma is close to 1, we're really summing all the rewards in the future, so we're doing a long-term planning. Whereas if gamma is close to 0, this would decay exponentially really fast, so we're just optimizing over a few steps. So it kind of determines how much in the future we want to actually optimize. So we applied this to the optimal control of these quantum heat engine in the following way. So at every time step I, the computer can choose an action which corresponds to choosing the value of the time-dependent controls U. And then we keep that U constant for a short time dt. The U would be this continuous parameter, for example, the gap of the qubit or some magnetic field that we apply to the system. And we additionally allow it to choose a discrete action di that corresponds to whether we want to couple our system, the quantum system, to the hot bath, to the cold bath, or just to the unitary evolution. And this is because typical cycles that are, for example, a Carnot cycle or so on, they always have like a hot stroke, a cold stroke, and an adiabatic stroke. So we want to allow the agent to potentially learn something similar. So it has to have this additional freedom of choosing the bath. And then we choose a state, at least in this work, we chose a state, the density matrix of their quantum system. And as reward, for example, if we want to optimize the power, we choose what is the average power that was delivered in the short time step dt. But then since the aim of reinforcement learning is to maximize the sum of all of these rewards, it will end up optimizing the average power over a longer time scale t, which depend on that gamma. Gamma was that discount factor in reinforcement learning. So if we choose this gamma close enough to 1, we're really optimizing the time average of the power over a very long time scale. Okay, so if we want to visualize how this works, we start from some state, let's say road 0, and the computer agent chooses this action, for example, choose this value of u, keep it constant for some time dt, and this color orange would be that discrete choice of coupling, let's say, to the hot bath. And then after we do this, we evolve the state for time dt, we compute the new density matrix, we get the power that was delivered in that short time, and based on this, the computer chooses, for example, change the value of u to u1, but let's keep it orange, which means still coupled to the hot bath. We get some feedback and so on and so forth. So in the end, we end up constructing this piecewise constant, let's say, protocol. So we applied this idea first to the most simple possible model of let's say a heat engine. So just we consider a 2-level system, and our control is simply the level splitting of this qubit. And this is what we found. So here we're plotting the power, the average power extracted from the system as a function of the training step. So a step here would be 1 dt evolution, just a very short time step. And here we show what are the actions, so what are the value of the controls that were chosen by the agent in these 3 points here during training. So for example, at the beginning here, we see that the actions U are completely random, the color is random, the position is random, and this is because the agent or reinforcement learning has no knowledge about the system, so it just chooses actions randomly, and the corresponding power is negative, which means that we're not extracting work, but we're dissipating work into the system.
Paul, let me stop you.
Yeah, sure. Yeah.
So you're trying to optimize power extracted from what? Can you go back to the diagram and show us again?
Yes.
What you're extracting?
Yeah, so it's the work that you extract from the temperature difference, let's say. So it's, yeah. So if
So
you,
you're trying to optimize the work done on a mechanical device, for example.
yeah, it could be,
So
yeah, the work that you can extract,
it's a standard,
exploiting.
standard heat engine.
Completely standard heat. Yeah, it's not a measurement heat end. It's just that you have hot, cold, and part of the heat going from hot to cold, you extract that as work. Yeah, exactly. Yeah, if you have any questions, please interrupt me if I'm going too fast, too slow, or whatever. And yeah, so this is just a regular power work power that you extract from a temperature difference. And yeah, we see during training, then this power eventually increases, some structure shows up in the chosen actions. And in the end, we converge to this, let's say, square wave control, where we just jump between the hot bath and the cold bath in this, let's say, square wave fashion. And in this previous paper, we actually showed analytically that this is the best solution, and the maximum power was this dashed line. So we see that at least in the simple case, we can reach what we knew was the correct solution analytically. So then we move to a system where we do not know what is the optimal solution, which is actually a model of this device that I talked about earlier, but we study it this time as a refrigerator. So this time we're putting work into the system and we want to extract heat from the cold. So we want to cool one of the two resistors. And again, here the control is this prefactor of sigma z, but now we also have this term proportional to sigma x. So now when we change the control UDT, the Hamiltonian doesn't commute at different times anymore. And this has a big impact on the system because you're generating coherence in the instantaneous eigenbasis now. And this introduces this effect that some people call quantum friction, so that if the Hamiltonian doesn't commute, you actually have some power losses due to the fact that it doesn't commute at different times. So we studied this case, and again, here we show the cooling power instead of the extracted work. And again, it starts off negative, then it reaches some maximum value, which corresponds to the cycle shown here as this black line. So we compared it to what was proposed in these previous papers, and they studied this trapezoidal cycle, which is given by this dashed line here. And we see that what we find is that the power found by the strange cycle is actually, roughly 5 times larger than what was proposed. And yeah, we could kind of interpret this advantage by the fact that this strange little jump that you see here is actually rotating the state of the qubit to minimize these power losses that you have due to quantum friction. So yeah, without any prior knowledge, it just finds a cycle that in the end we could interpret that it's reducing these power losses. And yeah. So then we studied the same system, but this time finding these trade-offs between power, cooling power, and the efficiency. So actually this coefficient of performance. So here we did this optimization many times, and each dot here is a separate cycle. So if you take cycles up here, you have high power, but you have a corresponding low efficiency. And as we move along this curve that is called the Pareto front, we go to solutions where we have higher efficiency, but we're paying the fact that we have a lower power. And to give an example, these are some cycles that were found, like this is the one that you have at maximum power, which oscillates pretty fast. And as you move here to solutions with higher efficiency, we go here to protocols that are slower and slower, which makes sense. If you want something more efficient, the cycle should be more adiabatic in some sense. And then we applied it also to a model of, so this is again a quantum heat engine. So the goal is again work, but this time the working fluid is if you want just a single particle trapped in a harmonic potential. So our time-dependent control is actually the confinement of the particle. And here again, what we found were these cycles shown as dots. And these are actually very similar to what was proposed here in literature and what they call to be autocycles. So an autocycle would be this trapezoidal line shape where you have a hot bath and you keep the control constant, then you do an adiabatic stroke, and then you do an isothermal stroke and so on. So what the agent finds are solutions that are very similar qualitatively, but there are some additional features that allow us to have this kind of higher power. So these red dots would be the autocycles. So we can kind of match the same efficiency, but we have some power advantage by doing these additional features.
Sorry, can we, what are the purple cross, what does RL previous mean?
Yeah, right. Yeah, this was a bit, okay. So what I showed in, for example, here where we just optimized the power, we were using a method that only used the density matrix as state. So the reinforcement learning agent could really look at the density matrix at every time step. And this simplifies the optimization because it has full knowledge of the state. But this is not experimentally feasible because you cannot measure in real time the full density matrix. So actually what we did in this follow-up paper, we were just giving the agent measurement of the heat currents in time, and we were not giving it any information about the density matrix. So we were assuming that the agent can only measure the heat currents and knows nothing about the quantum state. And so previous was what we found was the full knowledge of the density matrix, and these dots that are a bit noisy are without any knowledge of the state. And I think this shakiness is also due to the fact that it's harder to optimize if you don't know the state, so it's not perfectly, this should be a sharp curve ideally, but yeah, and here we were only optimizing the power, so in the end we find cycles that roughly have the same power, but since we added the efficiency into the cost function, it bumps up the efficiency quite a lot without sacrificing much the power, yeah. Okay, so to conclude, let's say this part, yeah, I just want to briefly mention that we also then recently did this work together with Andrew, Biebeck, Robert, and I think you already spoke about this, yes, so I won't say too much about it in this group seminar, but I think that, yeah, the main addition here is that we added the possibility of actually doing quantum measurements on the system and using the measurement outcomes as feedback to learn how to operate system. So I'd say the main difference here is that now we have stochastic measurement outcomes because we're measuring the system. And because of this, we cannot apply a fixed protocol anymore, but we have to really learn a feedback control strategy. So based on the measurement outcomes, we have to learn what to do. And this is a much more complicated task because it's not just repeating the same thing over and over, but based on what you observe, you have to change your behavior. And just as a very quick example, here we studied a 2-qubit device where we were measuring one of the 2 qubits. And we see here that the control that was applied as a function of time now has these kind of erratic jumps that you see from up to down. And the fact that we have these jumps is due to the fact that the measurement outcomes are stochastic. And based on the measurement outcome, then the agent kind of decides to apply a different control to the system. Okay, so yeah, I don't know if you have any question on this part before I move to the next or, okay. Yeah, so then we did something similar, but in the context of quantum batteries. So what does this mean? So forgetting the word quantum, battery is a physical system that I guess should have the following characteristics. We want to be able to charge it, so to transfer energy to it. And ideally, we want to do this fast. We need to be able to store energy, and ideally it should have a high capacity and remain in the system for a long time. And we want to also be able to extract the energy that we put into it at later time to get some useful work out of it. And what I'll focus on in this presentation is mainly the charging part and the work extraction. And then the idea is to understand if quantum effects can have an impact on the transfer of energy or on the storage of energy in quantum systems. And there have been reported in literature some advantages in the charging speed. So in these papers, they show that, I'll talk about this in the next slide better, but that there is some kind of collective advantage in the charging of these systems, which is not necessarily quantum, but it's still a many-body or a collective advantage. And there's also been a few recent experiments where they kind of test this idea, and okay, I'll show this more in detail probably in the next slide. So one model that was proposed in this paper was based on the Dickey model. So the Dickey model describes the interaction between a collection of atoms that are just described as 2-level systems inside an optical cavity. So this would be representing 2 mirrors, and you have the photons inside the optical cavity that are interacting with these 2-level systems. And here we interpret the cavity, so we interpret the photons in the cavity as the charger. So we imagine that we initially have a certain number of photons in the cavity, and this is the energy that we want to transfer to the battery, which is the collection of the 2-level systems. So we want to study the energy transfer from the photons to the 2-level systems, and we interpret these 2-level systems in some sense as the battery that we want to charge. So a fully charged battery would be all excited 2-level systems. And then we have a term in the Hamiltonian describing the interaction between these 2-level systems that are collectively coupled to the same mode. And in this experiment here, they claim that they tested pretty much this model. And here the 2-level system were these dye molecules that were confined in these 2 Bragg reflectors. So these behave essentially as the cavity. And they actually studied the energy transfer between the photons and these 2-level systems. So the advantage is the following. So if you imagine now that you have n battery units, in this case, n two-level systems, and each one is charged with its own charger, then clearly the power that you transfer to all of the n units will simply be n times the power that you transfer to a single battery. Because all these n units are charging independently, so the total energy you transfer would just be linear in the number of units. But now if you imagine that you couple all of them to the same charger, which is what happens in the Dickey model, because all the two-level systems are coupled to the same mode, in principle, you could have that the energy transferred to the two-level system is not necessarily linear in the number of constituents, so in the number of these two-level systems. And what they showed in this paper is that, and we would call it collective advantage whenever this exponent is greater than 1, so let's say nonlinear. And in this paper, they claim that, in the Dickey battery, you have this alpha equals 3/2, so you have essentially a square root of n enhancement in the speed at which you can transfer energy to these two-level systems. Okay, so more in detail to control let's say the energy transfer between these two parts, we need some time-dependent controls. So we studied two different controls. One is the detuning. So this would be a parameter that detunes the two-level systems from the frequency of the cavity. And we have one term that controls the switch on and off of the coupling between the two-level systems and the cavity. And then we assume that the initial state is simply given by the product of the ground state of the battery, so all the two-level systems in the ground state, times some Fock state or some state of the cavity where we have enough energy to ideally fully charge the two-level systems. And then we apply some time-dependent controls. We just solve the Schrodinger equation for some time tau, given these time-dependent controls. And then we look at how much energy was transferred to a single two-level system. So you can trace out the rest and take the density matrix of the two-level system. And you can ideally compute the energy that was transferred to this two-level system. Or more importantly, what we look at is actually the ergotropy, which is how much of this energy that is transferred to the two-level system that can actually be extracted from it. Because you could have some energy in the system that cannot be extracted. For example, if you have a thermal state, there's no way you can extract energy from a thermal state just acting locally on that state. You would be violating the second law. So in the same way, if this two-level system is entangled, so if it has correlation with the rest of the system and the state is not pure, you cannot extract all of the energy from it. So what we really optimize, in fact, is this ergotropy that formally is defined in this way as a maximum work that you can extract by doing, let's say, unitary operations that only locally act on this two-level system. Okay, so typically people studied this.
Pretty good. Can you say something about the form of the operators here? Like what's the interaction Hamiltonian look like? Things
That was, this is the model. So the charger part is just a harmonic oscillator mathematically. This would correspond to the cavity mode that is resonant or that is closest to the frequency of the two-level systems. The battery is just a sum of if you want sigma z or two-level systems that do not interact with each other. And then in the interaction, all of the two-level systems are coupled to the same cavity mode. So the qubits don't interact directly with each other, but they're all talking to each other by the fact that they're coupled to the same mode. So you could have these collective effects because of this collective coupling here. So the only way they talk is through that.
Coupling the same for all qubits?
Yeah.
Okay.
But I guess this is really hard to engineer because you'd have to have like one mode that uniformly
exactly.
each of the qubits in the same way, right?
Yeah, that's true.
The cartoon you draw is a bit deceptive.
We got the same comment from a referee that, in fact, I should have we updated the picture.
It wasn't me.
It wasn't. No, that means you're right. Yeah, exactly. The mode should probably be uniform over the two-level system. Exactly. Otherwise, this would not be a uniform coupling. Yeah, and that's another thing. So this model makes sense as long as you could have all the two-level system with the same coupling. If you start packing too many inside, then at some point you will hit a limit. So this is not an extensive thing. Okay, so typically people study, let's say, this on-off protocol. So where you just take the interaction, you increase it to some maximum value, you keep it constant for some time tau, and then you just switch it off after the charging time tau. This is just, let's say, some bang-bang control where you put maximum coupling for some time tau, and then you switch it off. And this is how, in fact, they identify this collective advantage. But then if you look at how much energy is actually transferred, it's just a percentage of the energy was transferred to the two-level systems. And this ergotropy is actually even lower. So I'll show in the next slide how much it is. So they show that for short time, you have this collective advantage, but then if you wait longer, you can't really fully charge these two-level systems. So what we wanted to answer in this paper is, can we do better with reinforcement learning? So by modulating these controls in time in some way, can we actually increase the energy or the ergotropy that we transfer to these two-level systems? And we do this in two cases. So in one case, we just tune this coupling parameter, this coupling control, and we don't act on the detuning. And in the other case, we act on the detuning, but we don't optimize the coupling. We could have done both together, I guess, but yeah, this was easier to start. So this is essentially what we found. So here I'm showing this ergotropy as a function of the charging time tau. And here the dashed line corresponds to the on-off protocol. So this is what happens if you just do this on-off and you switch it off after time tau. You see that you reach this peak, but then it actually goes back down to zero. And this peak only corresponds to extracting, I don't know, maybe 1/3 or 1/4 of fully charging the battery. So 1 is the maximum that you could transfer. So you only reach a small amount and then it goes down. Here, each color corresponds to a different number of two-level systems. So we considered numbers between, let's say, 10 and 20. And what we saw is that, yeah, using this reinforcement learning method, we could find now these solutions here where the ergotropy actually reaches a higher and higher value beyond the value of the peak, but we're paying the fact that we have to wait for a longer time. And this would be how the energy of the two-level system looks. So the energy is going to be larger than what you can actually extract from it. And again, you could roughly transfer 50% of the energy, but here we see that by modulating this coupling control, we could get larger values of the energy. So then we did the same in the detuning case, and we find something similar in the sense that we could get larger values of the ergotropy, but now we see that all these curves are kind of shifted off, or they're kind of offset. And this was actually in the original paper, this is the signature of this collective advantage. So this collective advantage is the fact that these peaks, even in the on-off case, are going to the left as you increase the number of n. So what they found is that as you increase n, the energy is the same, but the time it takes to reach that energy is moving to the left. So here, maybe it's not very obvious, but n equal to 20 is more to the left than n equal to 10. And what we find is that also in the protocols we find, it seems like this peak is shifting to the left. So if we rescale, for example, now the time with the square root of n, we see that all the curves roughly overlap. And the fact that they overlap, it means that we're still preserving this collective advantage, but we could do this reaching now a higher value of the ergotropy. And okay, now I didn't include the plot, but we could kind of relate this to the fact that the agent learns to mitigate the chaotic behavior of the Dickey model. So this Dickey model, apparently for strong coupling, is a chaotic model. So locally, these two-level systems eventually become a thermal state. And this is why this ergotropy goes down to zero, because at some point chaos kicks in and these two-level systems just become thermal states, so there's no work you can extract from it. And instead, by continuously modulating the control, it can avoid this onset of thermalization and keep it in these higher energy states. Okay, so now I'll just move to the last part, which I think is the shortest and simplest. So this is more in the spirit of this optimal design that I mentioned earlier of the system. So, and it's in the context of thermometry. So let's say we have some object and we want to measure its temperature. What you can do, you can take a thermometer, put it in contact with your sample, and if you wait long enough, it will reach a Gibbs state. It will thermalize with the object, and if it's, okay, heat capacity is small compared to this one, it will reach the same temperature thermal state. Now, if this was a quantum system, what we would have to do is to perform some measurements onto the system. We will get some measurement outcomes xi, and then we could build an estimator of the temperature from the measurement outcomes. And what is known is that from this quantum Cramer-Rao bound tells us what is the ultimate bound on the precision of the best estimator you can build doing the best quantum measurements on your system. So this M here is the number of measurements you do, and this is telling you that the precision of your estimator is lower bounded by this quantum Fisher information, which is a property of the system. And the question is, how do we saturate this lower bound on the precision? And what has been shown is that if you just want to estimate the temperature, the best measurement you could do is just an energy measurement. So you should measure the energy of your thermometer. And once you do that, the quantum Fisher information is simply the heat capacity of your thermometer. And so what this is telling us is that if we want a thermometer with minimum uncertainty, we need to find a system that has maximum heat capacity. And this maybe sounds counterintuitive, but the heat capacity in the end is the variation of is dE over dt. So it's how much the energy changes as you change dt. So if you want a sensitive thermometer, you want something that for small dt gives you big dE, so that if you measure the energy, you can pick up an energy change from a small change in the temperature. So if we go back to this picture, now we assign, let's say, some structure to the thermometer. We consider it just like a network of two-level systems or of spins. And what we want to understand is how do we choose the Hamiltonian for these spins to get a best thermometer, so the highest heat capacity. So what was shown already in this paper is that they did a full optimization over any possible Hamiltonian. And this would mean also introducing 2, 3, 5 body interactions, so unphysical interactions. But if you assume that you can engineer any possible Hamiltonian in the world, they showed that you should engineer one that has this spectrum, so just one ground state and a super highly degenerate first excited state. And in this case, then the heat capacity would scale as n squared. So usually the heat capacity is extensive, it's just linear in n, so it means that also the precision of the thermometer would just double if you double the spins. But if you can engineer this Hamiltonian, you have this quadratic advantage. So you would have that the precision now increases with the square of the number of two-level systems. However, it's not clear how to engineer these interactions to get this type of spectrum here. So what we wanted to answer in this work is how can we really reach this optimal value, making some physical assumptions. And by physical assumptions, I mean we assume that we only have two-body interactions and not 3, 4, 5. And then we try to answer, can we do this also with just local two-body interactions? So what we just consider spin network just of sigma z terms. We actually considered the case with also sigma x, y, and z, but we found no advantage in taking different, because I think what really counts is just a spectrum, and adding these extra quantum effects didn't really help us. But yeah, so we consider arbitrary values hi and arbitrary values of jij, and okay, yeah, these are the Pauli matrices. And what we want to do is figure out what are these values of hi and jij that give us the highest heat capacity. And this is the type of Hamiltonian that can be programmed, for example, on D-wave quantum computers. It's exactly this type of Hamiltonian. I don't think we could use it as a thermometer, but yeah, they really allow to tune these individual couplings and so on. So yeah, so what we want to answer is how to choose these parameters to get the best thermometer. So we start from a random guess of these values. Then you compute the Gibbs distribution. We can compute the heat capacity. Then we take the gradient of the heat capacity with respect to these parameters using this automatic differentiation, which is something that is often used in machine learning frameworks to just simplify the calculation of the derivatives. And then we do some kind of gradient descent approach, so something quite straightforward. And this is pretty much the picture. So here we plot the heat capacity as a function of n, which is the number of these two-level systems. And this is what is known. So here, this green line represents the best that you can do with non-interacting systems. So if these two-level systems don't interact, the best you can do is to have a linear increase. And this is, so this green region is what you can reach with non-interacting systems. This red line up here is this ultimate bound that was found in the previous paper. So we know that we cannot go above this region, but here we have this n-square scaling. And if you take, for example, the 1D Ising model, so just with a single 1D chain with nearest neighbors interactions, this is what you find. So you can do better than non-interacting systems, but you still scale linearly in the number of parameters n. So the question was if we can find something in here, and the answer was pretty much yes. So these blue dots here correspond to this model. So just by doing the optimization, we found that often we would find these solutions where there's one privileged spin coupled to all other ones. And this is what I think some people would call the star model. So you have one spin that is coupled to all other ones. And then since we found these structures, we could actually notice that we could study it analytically, and we proved that this has this n-square scaling. It's not the same as the bound, but for large n, it gets kind of asymptotically close to it. But the disadvantage here is that we have a strongly non-local interaction. So you have one spin coupled to all other ones. So this would be a very long range interaction that you probably can't do physically beyond maybe 5, 6, 7 or something like that. So then we imposed some locality on the interactions, and we found these other structures where you have like a chain of star models. So here we limited this number of M, now it's fixed, there's maybe like 3, let's say, and you find many of these little star chains connected together. And again, we have this quadratic scaling, but we lose something in the prefactor. So the fact that you go to local model still allows you to get this n squared, but you pay that you get a smaller prefactor. And okay, to be honest, then you actually have to scale the coupling strengths here with n. So as you increase n, you would have to also increase the coupling strengths, which again, at some point you would hit a physical limit that would limit this, but yeah. So that was it. Yeah, so we've seen in general, to summarize, how we could use, let's say, method from machine learning to solve problem in quantum thermodynamics, both in the control of systems. We've seen how we can control heat engines or batteries, or how we can design a thermometer. And yeah, I would say probably the opposite of a benefit. The disadvantage of machine learning is that it's a numerical method, so you don't get a nice analytical response. But aside from that, yeah, we often find solutions that work better than what was previously proposed by, let's say, human intuition. It doesn't require too much knowledge about the system, or some methods can really just do an optimization without putting too much physical insight. Sometimes you can learn from the solution. So like in the thermometry case, and we could see these structures emerge and then understand why they actually worked. Yeah, and these model-free extensions of reinforcement learning, you can in principle imagine to directly learn how to control an experimental device just by interacting with it, without even knowing what is the exact model of these systems. And it gives you also a robust framework to account for noise and uncertainties, which we haven't explored much, but yeah. And yeah, that's it. Thank you for listening. And yeah, if you have any questions, let me know.
Thank you, Paolo. Time for questions. Yes.
Can you go back to your star model there?
Yeah.
Yeah, in the next one too.
Okay, yeah.
So you told us correctly that the heat capacity is a variation of internal energy with respect to temperature effect.
Yeah.
Can you tell us why physically that we get this n squared scaling when you have these stars?
Yeah. So before thinking about the stars, so yeah, this was the spectrum of the that was shown to be the best one that gives you this n squared scaling. So what you do, you choose this gap in such a way that 50% of the population is in the ground state and 50% of the population is in this super highly degenerate first excited state. So you're at this very sensitive point, and now if you just change the temperature by a little bit, all the population collapses to the excited states. And if you decrease the temperature by a little bit, then the population all goes to the ground state. So you choose pretty much, so you have to carefully tune this gap here to be sensitive around a given temperature. And then it's really sensitive because here you have this exponential degeneracy. So you have like a 2 to the n degeneracy. And because of this, just a very small change in temperature will pretty much have a drastic change on the population of the ground state and excited state. And yeah, so this is kind of the idea. You're in this point. So if you imagine the occupation of these levels with a Gibbs factor, e to the minus beta epsilon, yeah, you're in 50% here, 50 there, and just a small change of temperature gives you this collapse of the population. And the star model can do something similar. So if you look at the spectrum of the star model, we have one ground state, then you have half of the excited states that are degenerate here. So we don't have 2 to the n, but we have 2 to the n half, the first excited degenerate, and then you have higher states that don't contribute much. And the way we can do that with the star model was the following. So you have to kind of carefully choose the value of the on-site H and the value of these B terms. So one thing is that you need this very high degeneracy. And the way we got this degeneracy was by the fact that here, when you, for example, flip one of these values of B, you get plus H from the local energy, but you get minus H from the coupling if this is in a given state. So by choosing everything appropriately, when this, for example, is pointing down, every time you flip one of these, you have a degenerate energy because you get plus H from the local field, but minus H from the coupling. So you really want to kind of choose the system that you have this huge degeneracy when the central spin is in one configuration, and when the central spin is in the other configuration, okay, you get additional states. But you still get this exponential degeneracy here. That is what was really necessary to get this n square, let's say. Yeah.
And so do you choose then that gap or the energy scale to match the temperature?
Yeah.
So you do that in order to get the maximum sensitivity for small changes.
Exactly. Yeah. Yeah, this, if you want, this is in fact is called local thermometry. So this means that you have to already assume that you know roughly what is the temperature that you're interested in, and you're just maximizing the local sensitivity around the given temperature. Then there's this global thermometry that is more worried with how to do this if you're interested to be sensitive in a larger interval, and then this would not be the best. So this is super sensitive around one temperature, but very dull. Yeah. Yeah, because once all the population collapses to the ground state or the excited state, there's nothing left. Yeah. Yeah, so probably would be interesting to find models that kind of trade between being locally sensitive or maybe more sensitive in a larger interval. Yeah, we didn't look into that, but that would be, yeah, probably more useful in practice. Then there are also like adaptive strategies. So one could think of using a different model to get a rough estimate of the temperature. And then once you have a rough estimate, you can kind of narrow down on it with these kind of models. But yeah.
Yeah, and clearly the degeneracy is a very special condition. So if you
Yeah.
look at all, if you break up this degeneracy a little bit, how sensitive this is to slight breakings of symmetry.
Yeah, so here the first author, Buser, he did a big study theoretical on all these kind of sensitivities. So it is, so yeah, it was kind of robust. So now I don't remember exactly the details, but we could have like a polynomial number of states between the ground state and this degenerate one. You could have as many states as you want above, as long as you have an exponential degeneracy in that first one, exponential in the number of qubits or two-level systems. And how aligned did they have to be? I think it was probably order 1 in the sense that it's like a constant. It doesn't scale with n. I think how much they have to be aligned. But okay, I don't remember now that detail. But yeah, so it was kind of robust to few states in between, many states above. Now I don't remember exactly the bandwidth, but yeah, we did look into that, yeah. Yeah.
In the reinforcement learning part, you mentioned that from an analytic expression, you got some like power out of it, like work extraction. But then when you did the reinforcement learning, you found almost the same thing, but a different level of like extraction. So why?
Yeah, so maybe let's see. Was it this one here you're referring to?
Yes.
Yeah, I mean, yeah. In fact, yeah, they look quite similar. There are these like additional jumps. So here, let's say this is unitary. So green means that you're decoupled from the bath and you're just doing unitary evolution. And again, I think here what's happening is that the specific unitary transformation that is being implemented by this control is again mitigating this quantum friction that is also present in this model. So here, when you change the control U, the Hamiltonian doesn't commute at different times. So you have some power losses due to the fact that you're generating coherence in the instantaneous eigenbasis. And here you're doing some unitary, let's say, stroke before switching from the hot to the cold bath. And by doing this, I think this gave us some advantage. In fact, if you see, the advantage is not huge. So the efficiency here, we can match the same efficiency, and the power goes from, let's say, 0.7 to 1 in these units. There's like a 30%. It's not a drastic improvement. But I guess just a small change here had kind of a 30% impact, let's say, with these numbers. Or here, for example, you're changing the control while you're coupled to the heat bath. So you don't decide to decouple. So you don't, let's say, waste time changing the control while decoupled, but you're doing it while you're still coupled. And yeah, in this case where you care about power, this was beneficial. And when you care about efficiency, it's important to kind of minimize this additional effect, something like that. Yeah.
Not this thing, Paolo, again.